Well, hello everyone. I hope you are doing well post Thanksgiving break. Um, I trust that you are whenever you're watching this, morning, evening, whenever. Hope that everything is going well for you. Um, we're going to start talking today about the sixth unit, which involves the periodic table. A little bit more laid back of a unit compared to the last one. If you're missing anything, please try to get that in soon. I'm doing my best to put in grades as quick as I can. It took me a very long time to grade that test for everybody, but I should, if you turned it in, I should have the grade posted already for that. And I'll get more stuff done today as well. So, moving on to chapter six today. Um, so, Yesterday, you were supposed to go through this unit with a book that I posted, every picture or every page from this unit in the book. And I think I'm going to keep doing that because that's a good resource to go back and look through as you're trying to understand this stuff or taking a quiz or test or whatever. So the first section is about organizing the elements. And so we're going to talk about how the modern periodic table came to be, who's the first person that discovered it, and so forth. So on the screen, you see the four learning objectives for this unit. You're going to see as soon as I get done talking about this section how the notes are going to change for this unit. And I'll have a question posted on Google Classroom and a poll to see if you all actually like this method better or if you like the other method better. And whatever one wins is the one I'll stick to for, I guess, the rest of the school year. So, the learning objectives for today, though, are to first explain how chemists began to organize the known elements. Second, describe how Mendeleev organized his periodic table. Third, describe how the modern periodic table is organized. And the fourth one, the last one, is to identify three broad classes of elements. Now, I would say a good portion of this you probably have heard before. There may be a few things we talk about today that you haven't, but once again, um, with physical science, with middle school science, a lot of this stuff you probably have heard before, but maybe not as much detail as we're going to go in. And I think if I click over, it's probably going to play this, but I'm going to let you all, yeah, I'm going to let you all watch it on your own. So that's my gift to you today. Um, so, how can you organize and classify elements? Yeah, that's what we're going to talk about. So the first topic in this unit is searching for an organizing principle. Okay, and when you see the notes in just a moment when I'm done talking about this, you will see how it's organized. Okay, so how did chemists begin to organize the known elements? Right. So a few elements, including copper, silver, and gold, have been known for thousands of years. Um, and by the year 1700, which was 320 years ago, there are only 13 elements that were identified. But other elements were expected to be, existed. And kind of when elements started being discovered, it kind of went pretty quick. So, and if it's in yellow, that means that you need to put it in notes, as you probably know that. Okay. So early chemists used the properties of elements to sort them into groups. Okay. So we need to know what um, is similar for these elements that are sorted into groups. Okay. So in 1829, a German chemist, J.W., I don't know how to say that, Doberiner, published a classification system. In his system, the known elements were grouped into triads. Okay. And so he's important, but he's not the most important person for this unit. The most important person for this unit is Mendeleev or Mendeleev, however you want to pronounce that. His periodic table. Okay, so we need to know how he organized his periodic table. Okay, so he was a Russian chemist and teacher, as you could probably guess by the last name, in that area at least. And in 1869, he published a table of his elements. Okay, and so he actually used note cards to tell the properties of each element, and he pretty much just messed around with it enough to try to get a system that worked. Okay, and it was called a periodic table. And we know the periodic table today, um, the elements are arranged in groups based on a set of properties that they have in common. So each group has properties that they have in common based on the number of valence electrons that they have in their outer shell. That's why they behave chemically the same way. And Mendeleev arranged the elements in his periodic table in order of increasing atomic mass. Okay, that is how he chose to do it, which is slightly different than right now, but we'll get to that. So Mendeleev arranged elements with similar properties in the same row. Okay, and I'm going to skip that. There were places in the periodic table that were left blank. And if you look at this image right there, there are some places that are left blank with question marks right there, as you can probably see throughout here, question marks and stuff. Um, he predicted elements existed there, just didn't know what they were. Okay, and the two elements between zinc and arsenic, which were two of the ones that he did not know existed, but thought existed, were gallium and germanium, which were discovered in 1875 and 1886. Okay, so pretty much she's like, hey, something exists here. I don't know what it is. And then two elements were found to actually exist there. So a lot of people started to believe that the periodic table was actually something that was going to be useful, and that he was legit, essentially, right? So how is Mendeleev's periodic table an improvement over the triad classification system? um, Mendeleev was able to actually have all the elements and not just put them in groups of three and actually arrange them in order of increasing something, which was atomic mass at that point. And it actually allowed the ability to know that elements were there but undiscovered. Okay. So Mendeleev's periodic table was useful. If not for that work, who knows what it would be like now. There could have been somebody that, came along and did it eventually. Yes, of course, probably. But we owe a lot of the way it's organized to Mendeleev, okay, first person to do it in that sort of way. But just like John Dalton and some of the other people we talked about, they're not always correct. We come back later and we realize this is not how it should be. And so the modern periodic table is organized a little bit differently than what his was. Okay. So in a periodic table based on atomic mass, iodine should come before tellurium since iodine has a smaller atomic mass than tellurium does. So what this means is if you look at a periodic table, whether it's online, the ones I've given you this year or whatever, and you look at the average mass, which you should know where to find that because unit 4 was over that. Just because you go one element to the next element does not automatically mean the atomic mass increases. It usually does, but it does not. And iodine and tellurium is an example. And I think cobalt, let me look at this periodic table. I think cobalt, yes, cobalt and nickel is another example. Cobalt's average mass is 58.93. Nickel's is 58.71. And nickel is one place to the right. So it doesn't always increase as you go left to right. Usually, yes, but not always. Right? So, um, the atomic masses weren't wrong. Like they were right numbers, but organizing the periodic table by atomic mass was not the right way to go, essentially. Okay. So he developed this table before scientists knew about the structure of atoms, and he didn't know that the atoms of each element contain a unique number of protons, which we know obviously to be the atomic number now. Okay. So you've learned that. The number of protons is the atomic number. And in the modern periodic table, elements are arranged in order of increasing atomic numbers. So in the Mendeleev, in his periodic table, they are ordered in terms of increasing atomic mass. But in the one we have now, we increase with the atomic number. And that is the way that we're supposed to go. Okay. So if you look at the periodic table down there, as you go left to right, it always increases by one. It does not matter if you start with hydrogen to go to helium. If you start with boron to go to carbon, every one is one more. And that's how we know it to be true today. Okay. So the elements are arranged in order of atomic number, which starts with hydrogen, which has the atomic number of 1. Okay, so we've already mentioned this, but there are 7 rows or periods in the periodic table, and each period corresponds to a principal energy level, which is a value for N. So N equals 1, N equals 2, N 3, 4, 5, 6, and 7 right there. So the properties of the elements within a period change as you move across the period from left to right. So if you go back and look at this periodic table or any periodic table, the properties of sodium vary, they're vastly different than the properties on this side, such as argon, chlorine, and sulfur. Okay, sodium is a metal that reacts with a lot of stuff, water, whatever, and it's a metal that's an alkali metal. It's cut easily with a knife. Magnesium is a little bit more tough, but it's still a metal, and aluminum is a metal. But whereas these over here, chlorine is a poisonous gas, sulfur is a non-metal, but it's still a solid, but it's a non-metal, and argon is a noble gas. They don't have anything in common. So the properties definitely change. Okay, and this gives the opportunity for this law to come into existence. When elements are arranged in order of increased atomic number, there is a periodic repetition of their physical and chemical properties, which is what periodic law states. Hopefully, yesterday you wrote that down or typed it, I guess. Right? So elements that have similar chemical and physical properties end up in the same column of the periodic table or group. Okay, columns are up and down, rows are left to right. Okay, so elements with similar properties are found in columns or groups. Okay, I'll usually say groups of the modern periodic table. So if you go back and look here, that means that elements in this group all share similar properties. Elements in this group all share similar properties as well. These are the noble gases and so forth. And we will learn here soon about the names of the different groups. Okay, so last thing we want to talk about today, I want to talk about with you are metals, nonmetals, and metalloids, which are the 3 broad classes of elements. Every single element on the periodic table will fit into one of these 3 categories. A majority of the periodic table is metals. It's like 75, something around there. It's in the 70% are metals, and most of the rest are nonmetals. There's a few metalloids. Okay, so as you look right there at the periodic table, um, most of it, oops, from here over, literally from here all the way over, except for hydrogen, they're all metals. Okay, and then everything over here is a non-metal, and then you have this area that bridges the gap between the metals and the non-metals, and that's metalloids. Okay, they have properties of both. So let's talk about them. So the 3 classifications of elements are metals, nonmetals, and metalloids. I'm sure you've heard this before. Okay? But as you go across the period, the properties of elements become less metallic and more non-metallic. What that means is, as you go across, like you would read a book, like you read anything, left to right, we'll start here with potassium. As you go left to right, these elements become more non-metallic, meaning they go from metallic to less metallic, and that's how they become non-metals over there. Okay. So the number of yellow squares, I knew it was somewhere around there. And the table shows that most elements are metals. It's about 80%. Okay. So a majority of the periodic table are metals. You should know that. Okay, so let's talk about metals. Metals are generally good conductors of heat and electric current. So conveniently next to me, I have from some experiment that I did with AP earlier and before Thanksgiving. I have magnesium metal right here. Um, Metals are generally, like magnesium, good conductors of heat and electric current. And you probably know this. Um, you know, every day we need heat for things. Like right now, it's very cold outside. I'm in this room and it's warm. It's good. We also need electric current. What you're watching right now would not be possible if there was not such thing as electric currents. Okay, So there are elements that are useful in that regard, such as copper and silver. They're good at electric current. You know, if you take out your phone and you were to open it, you have copper and you have silver in your phone. Okay, and we generally use copper more than silver, although silver um, is the better conductor of electric current, but copper is way more inexpensive. It's cheaper to use. So, all right. Um, so all metals are solids at room temperature except for mercury, and mercury is not good for you. So many metals are ductile, meaning that they can be drawn into wires. Meaning you could take a metal like copper. Magnesium is not the best one to do this with, but you can take metals and you can draw them into a wire. And also, most metals are malleable, like magnesium right here, meaning that they can be hammered into thin sheets without breaking. Okay, so aluminum foil, tin foil, all that kind of stuff are definitely metals that are malleable. Okay, you can make them into sheets and they're not going to break. So that's properties of metals. Here's some properties of nonmetals. So the blue ones are the nonmetals. So metals generally tend to, I mean, there are variations, but they tend to be kind of the same for most of them. But for nonmetals, there's a great variation because there's a huge difference between helium and sulfur, or carbon and neon. There's a huge difference there. Now, a lot of the nonmetals are gases at room temperature, okay, like chlorine, neon, argon, oxygen, nitrogen, krypton, xenon, all those. But some, and fluorine as well, some exist as liquids and gases, or liquids and solids at room temperature. Okay, so sulfur and phosphorus are solids at room temperature, and bromine would be a dark red liquid. Another solid at room temperature would be iodine. Okay. And the variation among nonmetals makes it difficult to describe one set of general properties that will apply to all of them. Okay, because you have things such as you see right here, diamond, which is composed of carbon, covalent. It's a covalent network solid. It's very hard, very, very, very high melting point. And some match heads are coated with phosphorus, which is a brittle solid. So I thought I had matches around here, but I don't. I'm just going to show you. Non-metals tend to have properties that are opposite of those of metals, which makes sense in life. If you have something that is, this and something that's non that, it's usually the opposite. So, in general, non-metals are poor conductors of heat and electric current. We do not use, these non-metals to apply current or whatever to our electronics or whatever we're trying to use. We use things as copper, silver, gold, chromium, things like that, silicon. We don't use sulfur, chlorine, bromine, whatever to do that. Okay. And solid nonmetals tend to be brittle, meaning that they will shatter if hit with a hammer. So you're not going to be able to beat them into thin sheets. And if you want to think about this, think about carbon in the form of graphite in your pencil. If you write too hard with your pencil, it's going to break. And that's why we have things such as pencil sharpeners, or that's why we have um, the actual pieces of lead with those mechanical pencils. So write too hard, it's going to break. Our last way to organize the elements would be metalloids, and there's a heavy stair-step line that separates the metals from the non-metals. As you can see right here, there are not many metalloids, just a few. Okay, so they border that zigzag line. They're going to have properties that are similar to both, such as like silicon, which are considered semiconductors. So some conditions, metals may or metalloids may behave like metals, but they also may behave like nonmetals as well, right? So a good example of that is silicon, right? So I think that's all you need to write for this. So I'm going to show you what the notes look like and explain them, and hopefully that will answer most questions here. Okay. So you will see this. okay, on the screen right now. So Unit 6 notes, chemistry, the periodic table. This is the whole notes for the whole unit, okay? But of course, you only want to fill out the first section today because that's as far as we have went. You want to write the 4 learning objectives, which are found right here, right? The second thing you want to do, searching for an organizing principle, okay? So you want to take what is in yellow here, okay? So a few elements, including copper, silver, gold. Yeah, yeah. Well, what I had said already. Okay. All this stuff that we went over. You see how right here it says searching for an organizing principle? Everything that's in yellow until you get to the next heading, like Mendeleev's periodic table, you need to write or type, I guess, here. Okay, I hope that makes sense. Searching for an organizing principle. You need to type this right here and this right here, right? And then when you get to this, well, then you are ready to go to this heading, okay? And then you would write this, this, all this stuff, this, this, that, and then you would get to here, today's periodic table, okay? And then you would type what is in yellow or what's contained in yellow between this and this until we get to nonmetals and metalloids. So you'd want that, 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 and that. And then when you get to here, it's the last part, metals, nonmetals, and metalloids. So you want all that stuff, okay? Right there. So that is what you need to type in, okay? Hopefully that makes sense. And maybe this will be easier for you than the way we've been doing it, or maybe it won't be. I don't know. We'll find out. So I hope you are having a great day. Your assignment for today is simply to watch this Ed puzzle. To complete it, I'm not going to put any questions in the Ed puzzle. Just watch the Ed puzzle, complete it. Um, and fill out these notes for today. And if you didn't do the assignment from yesterday, go back and do that. And if for some reason you didn't take the test from the last unit, please go back and do that soon. Okay. Hope you're having a great day. I will talk to you later. See you.